In one of the previous sections, we used a precipitation reaction to illustrate how to convert a molecular equation into an ionic equation. So what we'll focus on right now are one of the major class of reactions, and those are precipitation reactions. A precipitation reaction occurs in an aqueous solution because one of the products is insoluble. So we'll go ahead and write that down. A precipitation reaction occurs because one product is insoluble in water or in solution. So the precipitate is the insoluble solid of the compound which formed during the chemical reaction in the solution. In order to predict whether a precipitation reaction will occur or if a precipitate will form, when you're mixing the two ionic compounds, you need to know whether any of the potential products that may form are insoluble or not. So this is another application of the solubility rules, or that solubility chart that you already have. So we need to be able to predict. So predicting precipitation reactions. We're going to answer that question, well, what if? That is usually the most common question. What happens if we mix these two things together? Is anything actually going to happen? So let's see how we'd actually go about predicting whether one of these precipitation reactions will occur. Suppose that you mix together two solutions. One, we're going to mix magnesium chloride and silver nitrate. So mix magnesium chloride and silver nitrate. We can rewrite this potential reaction as magnesium chloride, so MgCl2, and silver nitrate, AgNO3. So how can you tell if a reaction will occur? And if it does, what products do you expect? When you write a precipitation reaction as a molecular equation, the reaction between the compounds, the reaction has the form of an exchange reaction. So in an exchange reaction, we'll define this, an exchange reaction, by definition, is a reaction between compounds. So a reaction between compounds that, when written as a molecular equation, appears to involve the exchange of parts. So it's a reaction between compounds that, when written as a molecular equation, that appears to be an exchange of parts. And what that means is that the cation, or the positively charged ion, will change places with the other cation of the other reactant. So in a precipitation reaction, the anions exchange between the two cations and vice versa. So let us assume that a reaction actually does occur between magnesium chloride and silver nitrate. If you exchange the anions, so let's just imagine for a second, we're just going to write this out as an unbalanced reaction just for a moment. But if we were to split this up into its ions, we'd get magnesium, 2+, and chlorine, minus, and Ag+, and NO3-. We notice that these positively charged ions, these anions, are going to switch place. So we're going to make the assumption that this actually takes place. So our products are going to be magnesium and nitrate. So magnesium and nitrate, and silver chloride, which would be this theoretical reaction if it actually takes place. So this is potentially what we could get. If we were to go ahead and balance this equation, we get magnesium chloride and 2 silver nitrate yields 2 silver chloride plus Mg magnesium NO3 2. So as we proceed, we verify that magnesium chloride and silver nitrate are soluble, and then check the solubilities of the products. So first of all, Rule 3 says that chlorides are soluble with certain exceptions, which do not include magnesium chloride. So we can predict that magnesium chloride is soluble. Rule 2 indicates that nitrates are soluble, so silver nitrate is soluble. The potential products are silver chloride and magnesium nitrate. So according to Rule 3, silver chloride is one of the exceptions to the general solubility of chlorides. Therefore, we predict that silver chloride is insoluble, and magnesium nitrate is soluble according to Rule 2. Notice that initially we didn't include any of these phase labels. We couldn't because we didn't know whether or not they were soluble in water. But we just verified that magnesium chloride is actually soluble in water, so now we can add the phase labels. So we have magnesium chloride, which is aqueous, and silver nitrate, which we also said was soluble in water, therefore aqueous. And silver chloride was insoluble in water, so we can write the phase label as solid, plus magnesium nitrate, which we said, according to our rules, was that it was soluble in water, therefore aqueous. We predict that the reaction occurs because silver chloride is in fact insoluble in water and precipitates from the reaction mixture. When we actually do this, we get a white precipitate of silver chloride out, which you can later filter out. But the molecular equation is a summary of the actual reactants and products in the reaction. So in order to see that it occurs on an ionic level, we need to rewrite the molecular equation as a net ionic equation. So you first write the strong electrolytes, which are the soluble ionic compounds in the form of ions, and leaving the formula for the precipitate unchanged. So we're going to take this equation and rewrite it as an ionic equation. So we're going to separate each one of these compounds into its ions, just like we did previously in the complete and the net ionic equations. So we'll go ahead and do that. We'll split magnesium and chlorine, or magnesium chloride, into its constituent ions. So we get Mg2+, which we said was aqueous, plus chlorine, Cl-, which is aqueous, plus silver, which is aqueous, plus nitrate, which is aqueous, to yield silver, Ag+. I'm sorry, we can leave this exactly as AgCl as a solid because we know that's a precipitate, plus Mg2+, which is still in solution, so it's aqueous, plus NO3-, which is also aqueous. So we can balance these according to how many chlorine ions there are. There are 2 over there, 2 silver, 2 nitrate, 2 of the silver chloride, and lastly 2 nitrate. So now we have a complete ionic equation. What we need to do is write the net ionic equation. So we'll label this one. This is the complete ionic, and we're going to write the net ionic. And we'll do that by canceling out the spectator ions. So the ones that actually aren't involved in the formation of this precipitate. So we notice we have free magnesium and a free magnesium. So we'll go ahead and cancel those. Chlorine is locked up in the solid, so we can't cancel that. Silver is also in the solid, can't cancel that. But we have nitrate, which are the same on both sides, so we can cancel that. So the the net ionic equation will just be the ions that are involved in forming the solid. So 2 Cl minus, which is aqueous, plus 2 silver, which is aqueous in solution, yields 2 silver chloride. So this equation represents the essential reaction that occurs when we have silver ions and chlorine ions in an aqueous solution. If silver chloride were soluble, a reaction would not have occurred. We need to highlight that, bold it, underline it, star it, whatever it is that you need to do. So if silver chloride, or AgCl, if silver chloride were soluble, then no reaction would have occurred. Exclamation point, bold it, highlight it, star it, whatever you have to do. If silver chloride were soluble, then no reaction would have occurred. When you first mix solutions of magnesium chloride and silver nitrate, you obtain the solution of 4 ions, which we found or saw earlier in our complete ionic equation. We have a mixture of magnesium, chlorine, silver, and nitrate ions, which are just hanging around in solution. If no reaction would have occurred, then they would have been soluble in water, and we would not have formed this solid precipitate, and we would not have had a reaction.